So who in the audience has heard of the Perseverance rover? All right, good. It's most of you. Okay. So for those of you that have not, this is the current rover that is going across Mars. And so it is what this says is the first step in trying to get samples from another planet back to Earth. Okay, so we'll go into like what that big arm is and why it's drilling into the rock, et cetera. So we've kind of done an intro, but I wanted to give, because one of the questions that I get asked is, how do you get to a point where you get to work on spacecraft? And how do you get to a point where you get to do things in terms of any kind of spacecraft for NASA, et cetera? And there is not one path. So I started out in the military. I had a business degree, which is not engineering at all, right? So it was, I was not going down that track. I went in the Air Force and I started to work on drones. So like the big unmanned aircraft. And I really fell in love with the science part of it and like how these work together. I went all over the world. And so part of that was like, okay, how do I continue that? So then I went into something called the Foreign Service, which is a diplomat, learned Chinese. So that was the second part, again, not engineering. And that language ability, it is, I think, harder than engineering in terms of just learning that skill. But then it also gave me just a diverse kind of route of going to be a JPL engineer. After that, I was at Montana State University. I was there for 7 years, and I ran a bigger research program that had to do with like national security areas, so Department of Defense and energy. And then went over to JPL, which is in Pasadena, California, primarily because I wanted to work on the Mars rover. And that was the one opportunity I had. So when you hear of like, man, I have to go to school and I have to do this, there are many routes to go. I have loved every career that I have done, so that top right, and then every single opportunity that I've had. And I currently love what I'm doing. That one on the left, that is the Europa Clipper spacecraft. And it is in something called a thermal vacuum chamber. So that test is going on right now. They basically put it in a big tube, and then they lower it to negative 180 C. And then they see, does everything work? They turn it on and they do all of that testing. And then you're wearing specialized gear like I'm wearing so that part of me does not end up on the spacecraft. That's what we don't want to have. And then I'll go over that top middle picture later on. Okay, so Perseverance. Let's see if this will start. So the one amazing, not one, but a key part of Perseverance was how do you communicate with a spacecraft in Mars to drill samples? So to give you an example, if I say hello to the rover, it takes 7 minutes one way. And then for the rover to tell me hello back, it's another 7 minutes minimum. That means it's 14 minutes to do anything. So none of the things that it's doing right now, I can't drive it. I can't use a joystick. It has to be automated. So when we built the rover, we had to write software scripts. We had to build hardware that would do all of this in an automated manner. I mean, just think about that in terms of, we look at like self-driving cars. Not even close, right? I mean, we have some sensors on it. This thing has sensors that allow it to drill into a rock that we tell it to, collect a sample, and then put it in the belly of the rover. So it's an incredible feat of engineering, and that engineering crosses from, if you like software coding, if you want to touch hardware, which is where I like to go. I like to see the hardware pieces of it. And having that ability to drive across Mars and then to collect a sample that we can retrieve later. This is all that we've done on Mars already. Mars is not new to us. And the United States is the only country in the world that has been able to deploy a rover and successfully drive it anywhere and collect science. If you think about it though, how do we communicate? I was talking about that 7 minutes. You have to have satellites. So we have satellites that orbit Earth. We also have satellites that orbit Mars so that they can help us communicate back and forth. So if you think about like, I want a picture, like how did I get some of these images? it sends it back. And it sends it back via those satellite links that go all the way back to our satellites and then go to many places across the Earth to collect that data. So again, we've been doing this for a long time. You kind of see the 2020 there. And then the next step is we did all this cool sample collection, and now how do we get it back? So we will talk about that in a little bit. The key part and the interest is are we alone? And I think that is a question that goes across NASA as well as JPL because we do robotics. And we want to see, like, are we alone and how to do that? So one of the ways is we think, well, we know that Mars had a much bigger atmosphere. We know it had lakes. And so we want to collect to see were there animals in those lakes and can we see that? And we can't really do that until we get the samples back. So this is Jezero Crater. It looks pretty large, right? But think about it I think there's a video I shared called, it's 7 minutes until you know whether or not the rover survived. So yeah, so if you saw that is why we picked Jezero Crater, because it had to, from space, go into the atmosphere, and then it had to find a place to land that it wouldn't explode, hit a mountain, hit a boulder, and it did that on its own. So we said, go. And then we sat there and said, I hope that our engineering was good enough that it could find its own path. And it did. I mean, that's just amazing to think about. We are that many miles away, and we can tell this spacecraft to do something, and it does it just by itself with the engineering. That was all done at primarily JPL and throughout NASA. So this is at JPL. This is what's called the engineering model. So the thing is, we have to keep testing, and we upgrade the software all the time. And so 2020, when this landed, when the rover landed, I had to do testing on the instruments to say, hey, is it going to work? Or if we had a problem. There's storms on Mars. So for example, we had a weather instrument that was damaged and broken. And so we were trying to figure out, hey, can we still use it? And how do we test it? And so this is called the Mars Yard. And it's just looks like what it is. I mean, that's just a garage door. And it goes out onto that sandy area that is similar to Mars. And so we test the instrument. It's got a radar. It's got all kinds of cameras on it. It's got a ground penetrating radar on the bottom. And so we test this on Earth. So if we're going to update the software, for example, we'll test it here first, and then we shoot it up. And it goes across space, and it downloads into the rover on Mars. All right, what I thought was really neat, being an Air Force guy, was that we did a tech demo to see if we could fly anything in Mars. And if you want to think about it, Mars is about 10% of Earth's atmosphere. So in order to fly a helicopter on Mars, it's like flying a helicopter 22 miles up in the air. Have you ever seen a helicopter fly that high? No. It's really hard. So that is the tech demo that was Ingenuity, and here it is flying. This is an amazing engineering feat in terms of how fast those rotors are going to be able to beat against the air for 10% of Earth's atmosphere. So this was an amazing success to show how high you can fly something. And that if we go to Mars, human beings, that you can have something that hopefully can fly you around. I mean, that's kind of the idea. And in terms of this was a smaller drone. It flew many, many times. And actually the mission just ended last month. One of the rotaries finally broke off, and so the mission ended, but it was kind of on its way out anyway. So this is the first time we've ever flown anything on another planet. So pretty cool. Okay, the other part of this is a selfie taken by Perseverance. So it has this long arm, and it's got a camera called Watson, and it was taking a selfie. It's actually like 37 images that this took, and then they kind of put it together. So it took a selfie because there's Ingenuity, and it wanted to see the helicopter, and then we put all of the images together to make that happen. So it's pretty cool because you can kind of see the tread marks. of the tires, and then we had Ingenuity land just right next to it. So it's the first selfie from Mars that we took. So you kind of think about it too, like what are the different environments? So I had just shown a picture of Clipper that we were doing thermal vacuum testing, really cold. And this is why. For Mars, this was like last week, it was -4 as a high. So you think Bozeman's cold, right? You think Big Sky's cold. It's not as cold as there. And so we have to be able to operate and be able to functionally work this thing at really, really low temperatures as well as storms. Sol is what we just call a Martian day. So it's a little bit longer than 24 hours. It's like 24 hours and 45 minutes. So when we landed, the first 90 days, we did 24-hour operations, and we did it by sols. So for 90 days, all of us were up for a lot of hours trying to do shifts. It was a crazy time, but it is trying to work on the Martian clock. All right, so one instrument, this is probably my favorite instrument that I was able to work on, is something called MOXIE. So what it does is that most of the atmosphere in Mars is made up of carbon dioxide. And so this instrument takes carbon dioxide and makes liquid oxygen. You need liquid oxygen to breathe. You can make it so that you can breathe into it. It's also a source to take for like fuel. So if anybody's watched The Martian, in terms of how they like the movie, in terms of how they're going to take off, this is how they do it. And so this was the first time we've ever done that for real, and it worked great. So this is kind of that possible future that we're looking at. So the other part to think about too is that when we launched Perseverance, it took 7 months to get there. And that's the fastest that you can get to Mars. So we had to time our launch so that we could get there in 7 months. Otherwise, it takes 2 years. So let's think about that. 7 months, and human beings want to go. 7 months in like a spacecraft that's maybe 500-600 square feet with 3-4 of your best friends. That's a long time to be sitting together. You kind of get tired of each other's jokes, right? It's a lot of time. So for this project, which I'm a part of, and in the finalists you'd hear next week for the next mission, which will start in April, is that this is a 600 square foot spacecraft. And what we're simulating is that we're going to do launch to Mars, but we do it in 45 days, just so that 7 months would be really long. But we do 45 days, 4 people, and so this is at the Johnson Space Center, and you're kind of like a ground astronaut. You're having to have the same skill set. You have to be able to meet the astronaut criteria, and so they want to see how do people survive together. It's more really about mental health, how do you get along? So they do 45 days, and you follow the International Space Station schedule, meaning you work 16 hours a day and you just sleep for 8, or you get downtime for 8. There's no privacy. You have to sleep. You sleep right next to each other. There's like a mesh net separating you. There's no door in the bathroom. You got to figure it out, right? You have a curtain. And so you get to do that for 45 days, and then they put some stress on you. They make you stay up for 36 hours to see how you'll react. And why? Because you're going to have problems if you're going to fly. And if you think about if you have to try to do that for 7 months, this is a good test case for that, okay? So it's pretty cool. I should find out. I'll be down there in May and June to do that. Some people might think that's not fun, but I actually think it's good for science and will be an interesting experience. So again, autonomous driving. We tell the rover to go to a certain point. It figures out how to get there. It will avoid rocks, or it will stop. It's sandy and it's windy, so you don't want it to get stuck. So we have all these sensors on it that will actually stop and say, hey, I don't think this is a good way to go. Or it will move by itself. This one is, JPL's motto is to dare mighty things. And so this is the parachute that was when it went into the atmosphere and it was trying to slow itself down. So this is the biggest parachute ever flown. And so we put dare mighty things on it. That's an actual picture from our engineering camera that looked up and took this picture. And just to show the capability in terms of what we were trying to do. All right, so that's Perseverance. We're gonna switch over to Europa Clipper, and then we'll take questions.
Thanks. All right, I am Kendra Cook. I am Justin's wife, or he's my husband. So it was interesting, he talked about his path to getting to NASA. I was on a much more direct trajectory. I always knew that I wanted to be an astronaut, that I wanted to work in space, and so I went right into college to study aerospace engineering. I got 2 master's degrees in astronautical engineering and computer engineering, went into the Air Force and started working on UAVs and then spacecraft after that. So I have had a much more direct path, but it's because I knew ever since I was little that that's what I wanted to do. I was born and raised in Great Falls, and like I said, went into the Air Force, did a lot of private industry after that, and I've been at JPL for about 8 years or so now. This picture in the upper right-hand corner is actually me commanding the spacecraft in the thermal vacuum chamber last week. So it's pretty fun to get to work with your spouse. I know a lot of people don't get to do that, but we enjoy it. All right, so I'm going to talk to you guys about Europa Clipper and why we're going to Europa. So NASA has put a ton of money and resources into going to Mars, but in my opinion, the most likely thing that we're going to find there is evidence of past life. We're not going to find actual life there. But on Europa, we think that there's actually a pretty good chance that there could be actual life going on right now. So there is a predicted warm ocean under a thick icy crust. We actually believe that there is more liquid water on Europa than there is on Earth. In fact, 2 times as much. And so for a moon that is the size of our moon, to have twice as much water as all of Earth is pretty incredible. It's all held underneath this big, thick ice crust. I'll talk to you guys about that and the instruments of how we're going to look at that. And we think that there's evidence of active geology there. So Hubble telescope took a picture of it maybe 10 years ago or so, and we believe that we're seeing plumes coming out from the cracks in that ice. And so that indicates something like an underwater volcano or something like that. So we think that there's active geology going on down there. We also believe that there's an atmosphere that has all the right chemical compositions that you would need to house life. So we believe there's oxygen, carbon, hydrogen, nitrogen, and we're gonna have instruments that's gonna go confirm that for us. So Europa Clipper is the NASA flagship mission that's going to go out and look at Europa. It's primarily managed by JPL, and we have partnerships with the Johns Hopkins University's Applied Physics Laboratory, APL, out in Maryland. There's 10 instruments on board the spacecraft, and we have 7 different partners. Most of them are universities or associated with the university that are developing those. So it's pretty cool because it's a really collaborative effort that we're doing here. We're going to fly out on a Mars-Earth gravity assist trajectory, a MEGA trajectory, and it's purely based on timing. So you are going to follow, I'm not actually sure which one of these is the laser beam, this one. So we start at launch in October. We're at like 7 months and a couple days. It is really soon. And we're going to fly by Mars, and then we're going to loop back around, and we're going to fly by Earth, and then we're going to slingshot our way out there. So we're basically using the gravitational pull from Mars and Earth to basically boost us out to Europa. So we're actually going to be in orbit around Jupiter, not around Europa. And as we go around, we do a couple flybys of 2 of the other larger moons, Ganymede and Callisto, which will help us shape our orbit so that we can change the trajectory with every single orbit around Europa to where after about 45 passes, we will have covered the entire moon, or just about the entire moon. So what's really cool is that we've got 45 passes. The farthest away that we fly by is about 1,700 miles. The closest is 16 miles off the surface. We get really, really close to the surface of Europa. And I'll explain why when we talk about the instruments and what we're trying to do there. So we actually, most of them are going to be about within 60 miles or so. So we get pretty close because we want to do in situ measurements. So I'll talk about that. All right, so this is the Europa Clipper spacecraft, and it's about 20 feet tall. So this is about 20 feet. It's about 300 feet long when you count the solar panels, and that's about the size of a basketball court. So this is not a small spacecraft. We're using solar power out at Jupiter, which there's only about 4% of the sun's power at Jupiter. So that's why these have to be so big. We have a magnetometer boom, which is about 25 feet. And I'm going to tell you why that is shortly. But it's a pretty incredible thing to see up close because it is really big. All right, so these are the 10 instruments that we're going to take with us on board the spacecraft. And we've got a whole host of remote sensing instruments, and these are all going to be instruments that are pointed down at the moon when we do our flybys. And they're doing things like taking the measurements of the UV spectrograph. We're going to look at the IR spectrum. We're going to do thermal imaging. The cool ones, in my opinion, are the in situ instruments down here. And these are actually the ones that are going to do real, actual measurements on the particles themselves. So we basically have one SUDA that is a dust analyzer and a plume analyzer. And so if we see a plume and it's coming up and shooting up into the atmosphere, we're going to fly through it, and it basically is like this giant mouth that gobbles up all of those particles and ingests them and then takes that data and sends it back so we can determine what exactly is in it. Is it water? Is it something else? What is that made of? So we're going to actually collect the real physical samples of the material. The instrument that Justin mentioned that he worked on is the REASON instrument. That's the basically a ground penetrating radar. So that is going to map the thickness of the ice. And so we think it's between 5 and 15 kilometers thick. And if we ever want to send a rover there to drill, we would want to send it to the thinnest part so we don't have to drill through the thickest part. So that's one of the things it's going to do. It's also going to basically make a topographical map of the surface of the ocean. So we can see, are there mountains down there? Are there volcanoes? Things like that. All right, so Europa is actually this little guy. Where am I at here? This little guy right here. And it has its own magnetic field, but it's tricky because it's also within Jupiter's magnetic field. So we have to account for both of those. And what makes it even trickier is that the spacecraft also has a magnetic field. So we had to do all of the pre-work to map all the different sources of magnetics on the spacecraft so that when we take the measurements with the ECM, that we can basically back out our own magnetic field, and then what we're seeing is just Europa's, or Europa's plus Jupiter's. And so one of the reasons why we put it on the mag boom all the way out 25 feet off of the spacecraft is to try to get as far away from our internal magnetic sources as possible. So we're going to put it like way out here, and that'll help us not get in here where it's really messy. All right, so this is a graphic. Sorry, it's a little bit dark in here, but basically this is an artist's rendition of if we were going to see a plume and we want to redirect the spacecraft to fly through it, this is what it would look like. And I think it's pretty cool to be able to say, hey, we saw this thing on our last flyby. We've got 2 weeks to hurry up and change our trajectory, send it to the spacecraft, tell it to go somewhere else, or to go back again to that same place because we want to look at it even more. And so the operations of the spacecraft is going to be really tight because we fly by every couple weeks, but that means you only have a couple weeks to do the analysis, replan, and then resend up all the commands that you would need to change the spacecraft's trajectory. All right, and that's it. That's what I have on Europa Clipper. All right, so we have a lot of time for questions, and we brought our helpful helpers, 2 of our kids, Kaylee and Savannah, and if you ask a question, you get some stickers. So we'll open it up. Yes?